Hi everyone, today a video looking at the energetics series, specifically looking at Hess's law. So the enthalpy change for some reactions can't be measured directly. Remember in the previous video of this series we talked that an enthalpy change was a heat change but measured at constant pressure. So it's just an energy change at constant pressure. But the enthalpy changes for some reactions we can't actually measure directly, like we saw in the previous video where we did some calorimetry, doing reactions in polystyrene cups and things. Sometimes we can't do that, we can't directly measure them. Now for these we have to use an indirect approach. We have to use enthalpy changes that we can measure directly to work out the ones that we can't. And the way we do this is to use something called Hess's law. Now essentially this is just an application of the first principle of thermodynamics, this idea of the conservation of energy, that we can't create or destroy energy. And Hess's law states that the enthalpy change for a chemical reaction is the same and it's independent of the route taken from reactants to products. So if I've got a reaction that goes from A to B, if that's the chemical reaction that I can't work out my enthalpy change for, if I know lots of other enthalpy changes that can get me to the same product, I can just simply essentially use that route instead. So rather than going from A to B, I might be able to go from A to C to D to E to F and then to B through a series of many more reactions. But essentially it doesn't matter how many reactions are, as long as I've started and ended at the same place, it doesn't matter which route I've taken, the overall enthalpy change will be the same. And so we can write this down as a very simple mathematical expression. If delta H1 is the enthalpy change that we're trying to measure, we can say that this is essentially just the other direct enthalpy changes that we can measure, delta H and delta H2 and delta H3, added together. So an example of Hess's law. If we take ethine, that's an alkyne, C2H2, being converted into the saturated alkane ethane, C2H6, this can happen by two different routes. The first is that we can get a direct reaction. So we take our ethine, what we call hydrogenate it, we add hydrogen to it, and then we end up here forming our ethane, C2H6. And these are all gaseous species. And let's say that's delta H1, that's our enthalpy change that we can't directly measure, and therefore we need to go through an other route. It can also happen through a two-stage reaction. Essentially, first, the ethine gets hydrogenated to ethene, the alkene, C2H4, essentially a partial hydrogenation. And then the second reaction is that ethene gets hydrogenated further to the alkane, C2H6. And you can see these are enthalpy changes here that we actually know the enthalpy change for. So delta H2 is negative 176 kilojoules per mole, delta H3 negative 137 kilojoules per mole. And so Hess's law states that the total energy change must be the same whichever route is taken. So whether we go through this one-step direct reaction or whether we go through this two-stage reaction, the overall enthalpy change of going from ethine to ethane must be the same no matter which route is taken. And we can show this on something that we call a thermochemical cycle. So this is what a thermochemical cycle looks like. Here we have our example that we saw on the previous slide. So we have ethine, the alkyne, the C2H2 on the left. And at the top I'm showing you the delta H1, that direct reaction. So plus 2 lots of hydrogen going to ethane, C2H6. But then here at the bottom, forming this kind of triangle shape at the bottom, I'm showing the indirect route, this two-stage reaction. So rather than going directly to the ethane, going first to the ethene, the alkene, and then being hydrogenated further up to the ethane. And so you can see here that I've put the enthalpy changes for those reactions that we do know, that's the two-stage reaction, underneath those arrows. And so we just draw out normal sort of reaction arrows between these sets of species. And so we know what delta H2 is, we know what delta H1 is. Hess's law, remember, stated that delta H1 is the same as delta H2 plus delta H3. So essentially we don't have to go across the arrow from delta H1. Imagine yourself walking, actually physically moving from molecule to molecule here. We don't actually have to move across that top reaction arrow instead we can find an alternative route. Let's say we're actually walking this and that route is blocked, we can't get through there. We can get to the same place, that ethane, by going the alternative route, which is to go through delta H2 and through delta H3. So instead of doing delta H1, we do delta H2 plus delta H3. That's where that equation comes from. And so we simply just have to add these two together. So that becomes negative 176 plus negative 137. And our delta H1 for this reaction comes out to be negative 313 kilojoules per mole. And that enthalpy change there is the same as doing the two-step reaction or the direct one-step reaction. So Hess's law, remember, states that our enthalpy change is the same and is independent of the route that we take between the reactants and the products. So we're going to look at lots of examples here of using Hess's law and Hess's cycles, or the thermochemical cycles. But again, it's good just to revisit the definitions that we talked about in the previous video, because these are where they're going to really come in useful for working out quantities. So we had our standard molar enthalpy of formation, delta HF, and this is the enthalpy change when 1 mole of a substance is formed from its constituent elements under standard conditions, or reactants and products in their standard states. So remember that the standard state of an element is the state that it exists at standard conditions, and the standard conditions are 298 Kelvin, 100 kilopascals, and 1 mole per decimeter cubed if it's in solution. And so simply, it's the enthalpy change when we have 1 mole. Again, remember the really key thing here is it's 1 mole of a substance being formed from its constituent elements. Key thing, as I said, is 1 mole. So if we write out examples of these equations, it could be the formation of carbon dioxide. This is formed from carbon and oxygen. And again, remember in the previous video I said that we have to always remember the standard state of our element. So think about how does that element exist at 298 Kelvin, 25 degrees Celsius, and at standard kind of room pressure. Carbon is a solid. Now, typically, carbon has many allotropes. Remember that an allotrope is essentially it's the same element, it's just that we have a different arrangement of the atoms, essentially. So carbon can exist as many different forms. It can exist as diamond, as graphite, as graphene. These are all based just on pure carbon, but they have very different structures. The graphite allotrope is actually used as the standard state. The graphite allotrope is actually the most stable thermodynamic one at room temperature and pressure. And so we typically write our state symbol for this as graphite, S for solid. However, we also have to remember how other things exist at room temperature and pressure. And so stuff like oxygen, hydrogen, we said in the previous video that oxygen never goes around as just an O atom. It's never on its own. It's always with another oxygen atom to make O2, dioxygen. We also know that hydrogen doesn't go around as just hydrogen atoms. It also goes around as just H2, 2 hydrogen atoms together. And so when we think about our standard state, well, oxygen technically exists in a standard state as O2. Hydrogen exists in its standard state technically as H2. So if we're making carbon dioxide, we make it from carbon, the graphite allotrope, and oxygen as a gas, O2. And this makes CO2 as a gas. Remember that we have to put our state symbols in, because it depends on what the standard state of our, the enthalpy change will depend on the state of our species. And the important thing is, carbon is we use the graphite allotrope. And again, as I said, it's only 1 mole of what's being formed on the right-hand side. And so sometimes there are a couple of examples where you can come across this where it might change. If you're given a reaction and when you balance it up, you actually end up with 2 moles on the right-hand side. There's 2 ways you can go about it. The first is just to divide everything through by 2. And so the second example here, we have hydrogen plus oxygen, so H2 plus O2. Remember, those are the standard states. Hydrogen doesn't exist as H at standard temperature and pressure. It exists as H2. Oxygen is O2. And that makes water, H2O, as a liquid. Now, we could have written this as 2H2 plus O2 going to 2H2O. However, that has 2 moles of H2O on the right-hand side. And remember back to our equation, it's the molar enthalpy, so therefore we need to have 1 mole. And so 2 ways you can either get around this. The first is just to divide the whole equation through by 2. This will typically mean that you end up having some fractions, some sort of not whole integers. So in this case, H2 plus half O2 is to H2O. Or you can do the calculation on the equation that we didn't alter, 2H2 plus O2 to 2H2O. But remember that the answer that you work out at the end is for 2 moles of water. And so if it asks you to work out the standard molar enthalpy of formation, you'd have to divide it by 2, because there's 2 moles and you want 1 mole. And the final example here is the carbon, oxygen and hydrogen coming together to form ethanol. So simply we take our elements in our standard states, and then that makes our product. So the product's ethanol, it's made up of carbon, hydrogen and oxygen, and therefore we need to have our constituent elements being carbon, graphite allotrope is solid, hydrogen, H2 as a gas, and oxygen, O2 as a gas. Balance it up, and here again I've balanced it such that we only have 1 mole of our ethanol, so that's a liquid, on the right hand side. Now formation enthalpies are usually negative, exothermic. Remember we said that when bonds are formed, energy is given out. When bonds are being broken, we have to put energy in. Now in all of these cases, typically we might break some bonds apart because we have, for example, breaking the H2 bond apart or breaking the O2 bond apart. Typically, formation enthalpies are negative because we've formed a lot more bonds than we've broken. And therefore, typically, we end up giving out more heat than we've taken in, and therefore they are exothermic, negative enthalpy changes. And the final thing to say is that elements that are in their standard states have an enthalpy change of 0. And so if we're doing the calculation like we saw when we do our Hess's cycle or our thermochemical cycle, if we have an element in their standard state, well, the standard enthalpy of formation of that element is 0 because it's already formed in that state. So the standard enthalpy of formation of carbon graphite is 0. The standard enthalpy of formation of O2 is 0 because it's already found as O2. We haven't had to form it from anything. It already exists like that at standard states and standard conditions. So we can also review our standard molar enthalpy of combustion definition as well, delta HC. This is the enthalpy change when 1 mole, again 1 mole, of a substance is completely burned in oxygen under standard conditions or reactants and products in their standard states. So again, the standard state is just the state in which it exists at standard conditions of 298 Kelvin, 100 kilopascals, and 1 mole per decimeter cubed if it's a solution. But we have this idea again of the 1 mole, so in this case we have 1 mole of what is being burnt on the left-hand side. And so some examples would be this enthalpy of combustion for carbon. So again, remember carbon, we put graphite, solid. We have oxygen, O2 as a gas, to make CO2, a gas. We could have hydrogen being burnt to make H2O, to make water. Or in the case here of ethanol at the bottom being burnt, of course we know that if we burn any sort of hydrocarbon-based molecule, that we end up with carbon dioxide and water. And again, state symbols are really important. So for that last example, we have our ethanol as a liquid, our oxygen, O2 is a gas, CO2 is a gas, and H2O is a liquid at standard pressure and temperature. And combustion enthalpies are always negative because we have to give heat out. This is an exothermic change. In the last video, we talked about the fact that combustion reactions are always exothermic. So combustion enthalpy changes are always negative. So we can now go through a few examples of what these kind of questions might look like. Now, the first type of question to consider is if the enthalpy change that you're trying to calculate is an enthalpy change of formation. Now, if this is the case, the question will ask you probably, what is the enthalpy change of formation of molecule B? And what it will give you is combustion data. So these questions tend to ask for one of these types of the enthalpies we've just talked about and give you the data for the other. So they'll ask you to work out the formation enthalpy, and they'll give you the enthalpy change of combustion of various species. And so the way to go about doing a question like this is at the top we draw out our Hess's cycle, our thermochemical cycle. So along the top we have our formation equation. That's our delta H1. If we go back to that formula of delta H1 is delta H2 plus delta H3. So delta H1 here is our enthalpy change of formation, or enthalpy change of reaction sometimes. And then we will be given the combustion products. And so the way to think about doing a question like this is if you're given the combustion data, is to write the combustion product. So to take everything that's in your formation equation and to imagine reacting it with excess oxygen. So that's why you can see at the sides here where we have delta H2 and delta H3, I put plus O2. So imagine reacting every element in that formation equation with oxygen. So for example, if hydrogen's in there, you'll form water. If nitrogen's in there, you'll end up forming nitrogen oxide and nitrogen dioxide. If carbon's in there, you'll end up forming carbon dioxide, and so forth and so on. And so what this ends up looking like for our thermochemical cycle here is that we have our formation equation at the top and then combustion products at the bottom. And therefore, because we are combusting the stuff that's in our formation equation, we draw our arrows for this thermochemical cycle going downwards, down to the combustion products. And so your delta H2 and your delta H3 will be enthalpy changes of combustion that you'll be given in the question. Now, Hess's law states that the enthalpy change is independent of the route that we take. So while we can't necessarily go directly across delta H1 across the formation equation, we can instead go through this kind of downwards route. So going down through the combustion products and back up to the other side of the formation equation. However, to do that, you can see the direction we have to travel is shown by that red curly arrow. And our actual black arrows that we denote for our enthalpy changes are both pointing down. So the arrow that represents delta H3 is actually pointing in the wrong direction. Now all we simply have to do is flip the direction of that arrow. And we can do that. We can just turn our arrow the other way around. However, when we do that, we have to flip the sign of that enthalpy change. If you go back to the first video of this series, we said that generally if we had a reaction that was exothermic in one direction, the alternative direction was endothermic. We can just swap the exo and endo around if we change the direction of the reaction. And this is an application of it here. If we flip an arrow, we have to flip the numerical sign of the enthalpy change, but the number still stays the same. We just change it from positive to negative or negative to positive. And so our Hess's law here would be delta H1 is delta H2 plus delta H3. That's our general Hess's law equation, but for this specific example, it would be that delta H1 is equal to delta H2 minus delta H3, because we've had to flip the delta H3 arrow around. So an actual example here, maybe the question asks for the enthalpy change of formation of ammonia. That's NH3. So I've written my equation here, N2 plus 3H2 going to 2NH3. Now you'll notice here I've got 2 moles of ammonia on the right-hand side. We'll come back to that at the end. So we have to write down our elements in their standard states. So again, remember that nitrogen in the standard states doesn't exist as N, it exists as N2. Hydrogen doesn't exist as H, it exists as H2, both gases. We then end up forming ammonia, that's a gas, and we balance our equation, so we have 3 lots of hydrogen forming 2 lots of ammonia. The question would then give you the standard enthalpy of combustion for nitrogen, for hydrogen, and for ammonia. And in these cases here, we've got nitrogen, so we're going to form nitrogen dioxide when we combust it. And we have hydrogen, so we're going to form water when we combust that in oxygen. And so we write those combustion products down at the bottom. And again, we have to make sure they're balanced. Everything has to balance in these equations, and so to balance it out, we need 2 lots of NO2 and 3 lots of water. And so Hess's law, as we said, states that delta H1 equals delta H2 plus delta H3. But, as we said in this case, to go that direction we want to go, the red arrow, we can't go across delta H1. So instead we have to go down delta H3 and up, down delta H2 and up delta H3. Our delta H3 arrow is pointing in the wrong direction. And so we have to flip that arrow round, and by flipping the arrow, we flip the sign of that enthalpy change. So in this case, it would be delta H1 is delta H2 plus the reverse of delta H3, negative delta H3. Or a simpler way of saying that, because of course a plus and a minus end up making a minus, is delta H2 minus delta H3. Now, in this case, if I'd worked out my answer, remember that the definition of our standard enthalpy of formation was that it was for 1 mole. And so this was an example I was talking about before, that if we have 2 moles, for example, on the right-hand side, we can either start by balancing our equations such that we have 1 mole. To do that, I'd have to have a half N2 plus 3 over 2 H2 going to NH3. You'd also have to half the combustion products, so you'd have NO2 plus 3 over 2 H2O. So you can do that. Some people don't like working with fractions, and so the other way to do it is to just have 2 moles on the right-hand side. But then at the end, you remember that you've worked it out for 2 moles, and the definition is for 1 mole. The standard molar enthalpy of formation means it's for 1 mole. So to divide your answer by 2. An alternative way to work out these questions, if you don't actually want to draw out a thermochemical cycle like this, is to use the equation that our enthalpy change of formation is the sum of the enthalpy change of the reactants minus the sum of the enthalpy change of the products. Now the way that I remember this is simply by remembering the word crap. That's C for the combustion data, R for the reactants, and P for the products. So remembering the word crap, we can remember that combustion data is reactants minus products, essentially. And so this is an example of working out an enthalpy change of formation when you're given the combustion data. And typically these kind of questions will always ask you to work out some kind of enthalpy change, and it's your job to see what data you've been given and then to work out how to draw these thermochemical cycles, what actually goes at the bottom. And in this case, because we're given the combustion data, the enthalpy changes of combustion, we write our combustion products. And we can either do it as this thermochemical cycle, or we can do it using that crap mnemonic. I generally find it's best to do it in a thermochemical cycle just to make sure you don't make any mistakes, but a really quick way to double check you've got the answer right is to use that idea that the combustion data is the reactants minus the products. The other example that's really common to see this time is if they ask you to work out the enthalpy change of combustion. So let's say they give you a molecule and they ask you what is the enthalpy change of combustion of that molecule. And so this time, at the top of our thermochemical cycle, we have our combustion equation. So this would be, for example, we saw earlier the ethanol reacting with oxygen to produce carbon dioxide and water. That's our combustion equation. And the data they'd give you in the question here would be the enthalpy changes of formation. And so this time, if we're given formation enthalpy data, we write the elements in their standard states at the bottom, and then we draw our arrows going up, because what our enthalpy change of formation values are telling us is, well, what's the enthalpy change of forming the various compounds? And so to do that, we have to start, remember the definition, this is why remembering the definitions is so important. The definition of the standard enthalpy change of formation is that enthalpy change when we form our compound from its constituent elements in their standard states. So we start at the bottom with the elements in the standard states. We put both arrows going up because we will have formation data, so forming those species that are involved in the combustion equation. And so then our combustion equation we can say is delta H1, and then we have delta H2 and delta H3 as our arrows going up, and these will be formation enthalpies. Now again, Hess's law states that delta H1 is delta H2 plus delta H3, but again we have to look at the actual direction of our arrows. So again, that red curly arrow is showing me the direction I can go. If I can't actually go straight across that combustion equation, if that's an enthalpy change I can't work out the value for directly, I can't go across delta H1, but Hess's law says that the enthalpy change, the overall enthalpy change of this reaction, will be the same no matter the route I take. As long as the reactants and products, the starting point and the ending point is the same, no matter what the route is, essentially it will be the same overall enthalpy change. And so therefore, if we want to go around this red arrow instead, going sort of down and then back up, you can see that this time it's the delta H2 enthalpy change that is pointing in the wrong direction. And so like we did before, we have to flip that arrow sign, flip the sign of the actual direction of the arrow, sorry. And by flipping that direction of the arrow around, we have to flip the sign again. Remember, if we flip an arrow's direction, we flip the sign of the number. And so an actual example here would be the combustion here of ethane, C2H6. So we write out our equation. Remember that typically we always want 1 mole on the left-hand side because it's the standard molar enthalpy of combustion. So 1 mole of whatever we're burning. So 1 mole of ethane, which is a gas, plus 3.5 lots of oxygen as a gas, goes to 2 CO2, standard state of that is a gas, and 3 lots of water, standard state of that is a liquid. So now once we've done that, we can then draw out our cycle. So we have our delta H1 there at the top, that's our combustion enthalpy that we're trying to work out. And then remember, if we're working out combustion data, the data in the question that will be given is the formation enthalpies. And so to do that, we write our elements in standard states at the bottom. And so if we just simply look at what the elements we have in that equation are, we have carbon. So we write this out as carbon. Remember, graphite is the allotrope we use, so graphite solid. We obviously have oxygen, so O2, and we have hydrogen. And so the standard state, remember, of oxygen is O2, standard state of hydrogen, H2. Again, make sure it's balanced, so we have 2 lots of carbon, 3.5 oxygens, and 3 hydrogens. And again, Hess's law states that delta H1 equals delta H2 plus delta H3. You can visualise that with that red arrow that's going round from the reactants to the products, but by going down and back up rather than straight across. But again, the delta H2 arrow points in the wrong direction, and so we have to flip the direction of delta H2. We also flip the sign of that enthalpy change. These enthalpy changes, remember, are the formation enthalpies because we're going from the elements in standard states up to the compounds. And so in this case, we would say that delta H1 was equal to the negative of delta H2 plus delta H3. Again, there's another mnemonic to remember, which this time is flipper. So this is if we have formation data, we do products minus reactants. So F for formation, P for products, R for reactants, flipper. And this is because the combustion enthalpy change is the sum of the enthalpy changes of the products minus the sum of the enthalpy changes of the reactants. And so again, I always prefer to do an actual thermochemical cycle and to make sure that I flip the arrow. And if I flip the arrow, I flip the sign of the enthalpy change. But it's a good way to just double check the answer and just to do the sum of the products minus the sum of the reactants and use that flipper mnemonic just to double check. So time to have a go at some examples of this. So if you'd like to have a go, pause the video and the answers will be on the next slide. So our question was looking at calculating the delta H of reactions. So sometimes they won't ask you specifically for a combustion or a formation enthalpy change. They will give you just a reaction enthalpy change. Clearly this though is a combustion enthalpy change because we're taking methane, CH4, reacting with oxygen and forming our combustion products of CO2 and H2O. And we were given the key thing to look for is what data are you given? And so here you can see in the table on the right of that question, we were given delta HF, formation enthalpy values. So to calculate this, I'm going to do the thermochemical cycle method. And so remember that if we are given the formation data, the formation data is from the elements in standard states to the compounds. We have the compounds in the top equations, so we have to write our elements in their standard states at the bottom. And so we have carbon as a solid, as graphite, hydrogen as a gas, and oxygen as a gas. Remember, it's H2 and O2, not just H and O. And then we also have to balance it, so the equation was already balanced. The equation in the question was already balanced, but we need to balance this bottom equation down with the elements. So 2 lots of H2, 2 lots of oxygen. Then we can think about the arrow that is green as being the actual direction that we want to go. But our red arrows, which remember go upwards because we are forming those, we're given formation data, so we have to go from the elements to the compounds, so the arrows go up. You can see that the delta H2 arrow is going in the wrong direction. The delta H3 arrow is going in the right direction. And so the way that I always do it is to do it in stages. So first of all, to work out what delta H2 is simply the sum of all of the formation enthalpies on that left-hand side, on the reactant side, essentially. So we were given that the enthalpy change for formation for methane was minus 75 kilojoules per mole. You weren't given what the standard enthalpy of formation of the oxygen, O2, was. And the reason is because if you remember from earlier on, elements that are already in their standard states have an enthalpy change of formation of 0. So we can't form O2 from O2. The oxygen already exists in its standard state as O2. In that top equation, we have it as O2, and therefore it's already formed, so it doesn't have a formation enthalpy. It's an element in its standard state. Then delta H3 is just the sum of the formation enthalpies on the right-hand side. So we have the CO2 being negative 393 kilojoules per mole. H2O is negative 286. This is why it's important to balance the equation, because we have to multiply those values by how many moles of that we have. And so we do negative 393 plus 2 lots of negative 286. The total of that comes out to be negative 965 kilojoules per mole. So then we can think about actually working it out. So remember that Hess's law would state that delta HR is delta H2 plus delta H3. But in this specific example, our delta H2 arrow is going in the wrong direction. So we flip the direction of that arrow, we flip the sign of that enthalpy change. So we now have plus 75 kilojoules per mole for delta H2 essentially. And so our reaction enthalpy becomes negative delta H2 plus delta H3. And so that's negative 75. Remember that 2 negatives end up making a positive, so that's positive 75 plus negative 965. And the answer to that comes out to be negative 890 kilojoules per mole. And that's what we expect. It's a combustion equation here. It's essentially a combustion enthalpy change. These are always negative. The next example is to have a go for calculating the reaction enthalpy for the following one. So again, pause the video and the answers will be on the next slide. So this time, again, we were just given it as a reaction enthalpy to calculate, a standard reaction enthalpy to calculate it. However, we can quite clearly see that this is a formation equation, essentially. We're taking the elements in their standard states and forming a compound. So that's carbon as a solid, graphite. Here I haven't shown the graphite, I've just shown it as a solid, but it would be a graphite allotrope, plus 2 lots of hydrogen as a gas, going to methane, which is a gas as well. And again, we look to see what data we were given. Here we were given delta HC values, enthalpy change of combustion values. And so we know, if we think back to our definition, the enthalpy change of combustion is when we burn 1 mole of our compound, completely burn it in oxygen. And so we have to take the elements that we have in our formation equations right at the top and think about combusting these individually. And so we think about what happens when we combust carbon and what happens when we combust hydrogen. Now these are the standard combustion products. So by combusting carbon we get carbon dioxide, that's a gas, and by combusting hydrogen we get water, which is a liquid. And so remember, the standard states are there, gas for carbon dioxide and liquid for water. Again, make sure it's balanced, so 2 lots of waters. And then we can imagine our green arrow again as being the actual sort of Hess's law, if you like, the idea that if we can't go across the delta HR arrow, instead we can go down delta H2 and up delta H3, go around that way. So delta H2 is the sum of the combustion enthalpies on the left-hand side. And we were given the combustion enthalpy for carbon as a solid was negative 393. We're given that the combustion enthalpy for hydrogen as a gas is negative 286. Again, we have 2 moles of hydrogen, so we have to multiply the value for the hydrogen by 2. And so we end up with negative 393 plus 2 lots of negative 286, gives us a delta H2 of negative 265 kilojoules per mole. And then delta H3 simply, because there's only one product, is just the negative 890 that we have for the enthalpy change of combustion of methane. So we then have to go back to our arrows, and we know that if we're going to follow that direction, we have to flip the delta H3 arrow. It's going in the wrong direction, so we flip the direction of it. You flip the sign of delta H3, so delta H3 is now technically plus 890. And so we can say that our delta H of reaction is technically delta H2 plus the negative of delta H3, which is negative 965 plus 890 now, because we flipped the sign. And so therefore it comes out to be negative 75 kilojoules per mole. And again, what we expect, because most formation enthalpies are also negative. Now the final thing to talk about, again we've seen these in the previous video, are these things called enthalpy diagrams. This is where we show on the y-axis our energy or our enthalpy. On the x-axis we have our extent of reaction, or sometimes called the reaction coordinate, essentially just the progress of the reaction. And then we show, relative to one another, whether our reactants or our products are higher or lower in energy. And so we saw, I won't go into too much detail on this again, but we saw that an exothermic reaction, remember that we give heat energy out from our system. So the products end up with less energy than the reactants had. So the products are lower down than the reactants, and we can draw an arrow for our delta H, our enthalpy change, going downwards. Therefore our enthalpy change is negative and heat is given out. Likewise for an endothermic, our products are higher up than our reactants because we've taken heat in from the surroundings. The system now has more energy, and so our products go higher up than the reactants, and we can draw our delta H arrow going up. That's a positive delta H, and therefore heat has been taken in. And the reason I bring these up is because you can also do these Hess's law calculations not by using the thermochemical cycle or remembering the mnemonics we talked about earlier, but also drawing them out on an enthalpy diagram. So if we think about some examples of this, if a substance has less enthalpy, i.e. it's got less energy than another, then we say it's more energetically stable. So essentially, the lower down something is on an enthalpy diagram, the more stable it is. The lower down it is, the more stable it is. Now, the enthalpies of all elements in their standard states, we've said this before, the states they exist at 298 Kelvin, 100 kilopascals, and 1 mole per decimeter cubed, are taken to be zero by definition. So this was this example of, if you wanted the enthalpy of formation of carbon as a graphite solid, it would be 0. The entropy of formation of hydrogen as a gas would be H2 as a gas would be 0. O2 as a gas would be 0, because that's how they exist already, and therefore you can't form them if they're already formed, essentially. But we can draw these examples out as enthalpy diagrams. The example that I'm going to give here is on the right. So this is essentially this kind of isomerization reaction here of dimethyl ether, CH3OCH3, as a gas, converting into ethanol. This is just a functional group isomer of it, so C2H5OH, which is a liquid. And so let's say I don't know what delta H1 is. Well, I can apply Hess's law, and let's say that we were given the formation enthalpy values. If we're given formation enthalpy values, we know that we have to start at the bottom with our elements in their standard states, draw our arrows going up to form the compounds. And so let's say that the values that we were given here are delta H2 is negative 184 kilojoules per mole, delta H3 is negative 277 kilojoules per mole. So Hess's law states that delta H1 is delta H2 plus delta H3. Again, we need to look, so a red arrow that I've drawn there is the direction that if I can't go across delta H1, I need to go down delta H2 and up delta H3. However, the delta H2 arrow is pointing in the wrong direction, so flip the direction of the arrow, flip the sign. So in this case, delta H1 is the negative of delta H2 plus delta H3. And so you put those numbers in and you have positive 184 plus negative 277. And that comes out to be negative 93 kilojoules per mole. So again, it's an exothermic reaction. However, we can also draw it out on an enthalpy diagram. And the way to do this is to remember that our elements in their standard states, what we actually draw at the bottom of our Hess's cycle, have by definition, their enthalpy is taken to be 0. And so that becomes our 0 line on this enthalpy diagram, essentially, the 0 line right at the top. So we have our 2 carbon as a solid graphite, 3 hydrogen H2 as a gas, and a half oxygen O2 as a gas. We were then told that our formation enthalpy of the ethanol, C2H5OH, was negative 277. Now, negative means we go down, and so we have this here. We have this arrow that goes here. I've drawn it as a double-headed arrow just to show you the difference between the two, but really it's actually going down to form C2H5OH as a liquid. We can also draw another arrow which shows the negative 1H4 formation enthalpy of the dimethyl ether. That's 184, so slightly less. You can see there I've drawn it to kind of almost like 2/3 the way of that 277. And so what that means there is that therefore the arrow that is showing you the difference between the C2H5OH and the CH3OCH3, that's our enthalpy change that we don't know, the delta H1. And if you work out that's simply the difference between the 277 and the 184, which comes out to be 93 kilojoules per mole. Now, I personally prefer to do them as actual Hess's law cycles because, again, if you do it on this enthalpy diagram, it's not necessarily always clear whether that 93 is positive or negative. We know from the Hess's law that it's definitely negative. It's an exothermic reaction. A way to think about that is to know that we're starting from CH3OCH3. We're going to C2H5OH. So we have to think about, well, how do I get from, on the enthalpy diagram, from the ether to the alcohol? And that would be an arrow going down, and therefore it would be exothermic. But personally, I prefer to do it as a Hess's law cycle, and I would recommend doing it that way as well. So a final question to have a go at then. You can do this however you want to do it, whether you want to use one of the mnemonics, the Hess's law cycles, or the enthalpy diagrams. But have a go at the question, and the answer will be on the next slide. So the example we have here is we have lead nitrate decomposing to form lead oxide, nitrogen dioxide, and oxygen. So this is an example of a thermal decomposition reaction. So we can draw out our Hess's law cycle. So we have our reaction at the top. Just double check it's balanced, and it is balanced. Everything has to be put down with the state symbols. So solid for the lead nitrate, it's an ionic solid. The lead oxide is also an ionic solid, so a solid. And then the nitrogen dioxide and the oxygen are gases at standard temperature and pressure. So we have our delta H of reaction at the top. And then we look to see what data we were given, and we were given delta H of formation values. So remember, if we're given that, think of the definition. It's the formation of 1 mole of a compound from its constituent elements in their standard states, and therefore we need to take our elements in their standard states right at the bottom and then draw our arrows going up because we're forming the compounds at the top. And so we simply look at that top equation and we look at what elements we have. We have lead, we have nitrogen, and we have oxygen. So we write them down in the standard states. So lead exists as a solid, nitrogen exists as N2 as a gas at standard states, at standard conditions, sorry, and oxygen exists as O2 as a gas. And again, just make sure it's balanced. So then delta H2 is simply the enthalpy change of formation of the lead nitrate, negative 452 kilojoules per mole. And then the delta H3 is the sum of all the formation enthalpies of those products. So the formation for the lead oxide is negative 217. You'll notice then that we need to then find, we weren't given in that table, what the actual enthalpy change of formation for the NO2 was. This is a slightly different type of question where we're not calculating what delta HR is, because we were given it, we were told in the question it was plus 301 kilojoules per mole. Here we need to actually work out what the enthalpy change of formation is. It's a very similar way that we go about it to the previous questions, just that we need to do a bit of rearranging of our equations. So we know that delta H3 must be negative 217 for the lead oxide. The half oxygen won't have a formation enthalpy because it's already formed like that in the standard state, so therefore it's 0. And then we know that we're going to have 2 times whatever the value of formation for NO2 is. 2 because we have 2 moles of it. Again, my blue arrow here is depicting the way that I would go around this if I didn't know what delta HR was, essentially the application of Hess's law. And so Hess's law would say that delta HR was delta H2 plus delta H3. It's independent of the root. We can go down and up rather than just across. However, we need to flip the direction of the delta H2 arrow to make that go in the right direction. And so by flipping the direction of the arrow, we flip the sign of that enthalpy change. So delta H2 was negative 452. By flipping the sign, it becomes positive 452. And so our actual Hess's law arrangement here is that delta HR is negative delta H2 plus delta H3. So we were told that our reaction enthalpy was 301. So it's therefore equal to plus 452 plus negative 217 and then plus 2 times this formation enthalpy of NO2. So again, you can see I've used lots of brackets here. These personally just help me keep track of my signs, because there's obviously going to be a lot of sort of positives and negatives all mixing together. And so by using the brackets around the actual values, it just helps me sort of keep the signs nice and tidy. And so we can then write this a bit more neatly. So we have 301 is equal to the positive 452. Then we had plus negative 217. A plus and a negative is the same thing as just a minus. So negative 217. And then plus 2 lots of that formation enthalpy of the NO2. So we can just do that sum that we have there in the middle, the 452 minus 217. That comes out to be 235. So our equation now becomes 301 is equal to 235 plus 2 lots of that formation enthalpy. And then we can minus 235 from both sides. And what we end up with is that 2 lots of our formation enthalpy equal 66 plus 66 kilojoules per mole. And then because we want the standard enthalpy formation of NO2, that's for 1 mole, remember, due to the definition, we divide by 2 and we find that our standard enthalpy of formation for NO2 is plus 33 kilojoules per mole. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.